nothing changed, I don't know why, that's how the line
But
Yeah, we can talk, and I
Don't
may not
adjust
be
it.
able to, yeah,
I'll
maybe
try.
we'll do it, but it doesn't matter.
Anyway, we'll talk, catch up.
All right, are we ready?
Yeah,
I am the timekeeper, so.
Okay.
all right.
So you're gonna cut me off if I go over anything
No.
that you've done, alright.
She's been very generous.
Okay. I probably won't go over the 20 minutes. My goal is like not go too quick. That's honestly the
Right,
goal.
and we were thinking that, yeah, 20 minutes actually almost too long, I think, for a pitch for, but we have the 1 minute elevator
Yeah.
pitch to start with, and then we'll do the 20 minute, up to 20
Up
minutes,
to
20.
hopefully shorter, and then we'll do another about 15 to 20 minutes Q&A after that,
Perfect.
okay?
Alright, great.
All right.
So, okay, let's see, whenever you're ready.
Hi, my name is Randall Autry, and I'm a founding member of Aavet Therapeutics. At Aavet Therapeutics, we are developing a safe and effective immunotherapy program for the prevention and treatment of cancer. Specifically, we are using tumor antigen cells delivered via a patented technology to induce an immune response that, that ultimately seeks out and destroys tumor cells in the body. It is our long-term goal to be in both the human and companion animal marketplaces. Some quick facts about cancer that I wanted to kind of let everybody know about. This is from the American Cancer Society. About half of men and 1/3 of all women in the United States get cancer. It's approximately 1.7 million new cases of cancer per year. It is the second most common cause of death in the United States behind heart disease. And the current three main treatments for cancer are surgery, chemotherapy, and radiation.
Okay, I'm sorry, that, when your first thing,
Oh, you need me to start over?
yeah, no,
Okay.
you can, I had it down for a minute for your
Oh, yeah, I know.
pitch, but that was,
Yeah.
you did that fine. So
Okay, good.
Now we're starting the.
Okay, cool, all right. So the cancer facts. As I previously stated, our goal is to develop a minimally invasive therapy for the prevention and treatment of cancer. Our solution is a safe and effective immunotherapy program, so it's kind of a derivative off of gene therapy, using standard immunization procedures, a shot. What is gene therapy? Gene therapy is the delivery or incorporation of normal genes to replace a missing or a broken gene in the body to correct a genetic disorder. And what we are doing is we are taking this kind of one step further, and we're using gene therapy as the, so we're using AAV, adeno-associated virus, is basically a transport for tumor antigen cells, which triggers an immune response. And what we're basically trying to do is convince our immune system, which is kind of our best weapon against disease, to seek out and destroy specifically tumor cells in our body. So that's why it's the immunotherapy component of it. How does gene therapy work? What it is imagine just like we use a naturally occurring virus. It's called adeno-associated virus. We all have it. It's common throughout. The only thing is it's not harmful to us. And we can modify this as a mechanism to transfer a specific product that we want, to go to a specific area that we want, to get an action that we want. And we've modified this virus. So what we've done is we've taken the virus and we've taken kind of the signals off of it so that it allows for a smooth, uninhibited transfer to the actual tumor antigen to trigger the immune response. Is AAV safe? AAV is safe. Like I said, it's in all of us. We all have it. There have been plenty of studies that have already happened with this. The NIH no longer kind of views this as like a special topic. It's already been granted breakthrough status. So it's there. You know, a lot of people don't know this. UF should be really known for really two things. Everybody knows Gatorade. Gene therapy is the other thing UF is known for in the academic setting. So it's very common. It's done a lot here in Gainesville specifically. What distinguishes AAV, or Aavet's AAV technology from the others? There's two main problems with current AAV technology out there. One, it's not, there's waste. It's not as effective as it could be. And the other is since it's not as efficient, it gives us less gene expression. And the gene expression is the ultimate thing that we need to get the immune system to attack the tumor cells that we want. So right now, here's normal AAV right now. So you can see it comes in and we lose the prednisone acts on these little signals right here. And it causes us to have waste. This is really waste. We don't get much into the cell that we want, into the DNA right here. So what we've done is we've modified the coding on this little caspid right here, and we've used a couple promoters, so we no longer have the waste here. It's very minimal, and it goes into the DNA, we get RNA, and we get protein. And that's the key to it. So we get the protein to express, and then that triggers our T cells and our B cells to come in and attack the tumor cells that we need to get rid of in our body. This is all done using a dendritic cell. And dendritic cells are very important because it creates the antigen, it's the antigen presenting cell, which ultimately is the signal out to our B cells and T cells to say, hey, come help, destroy what's in here. And so if we come back here, this is where we get the expression. So we use, this is really a dendritic cell, and we're getting the protein expression there. So we've developed an optimized vector for specific antigen gene expression in dendritic cells. So antigens are important because that's what triggers our antibodies to act, which therefore do the assault on the invading tumor in our body. And what we've done is we've got it so that we can get this delivered via a simple needle injection. So it's not like you have to go under surgery. It's like no different than a flu shot immunization process. It's the same concept there. Our commercialization strategy for Aavet Therapeutics is to start in select cancers. So the most common ones we're going to go for are breast, prostate, melanoma, lymphoma, osteocarcinoma. But really, our step depends on the availability of antigens. That's kind of one of our barriers that we got to work on. It's not that we can't get them. It's just we got to find the right ones to trigger the responses we're looking for. So that's like the overarching thing. We're going to focus on specific cancers rather than going on a whole bunch of cancers. We're going to go on very common ones that are going to be easier to solve, so to speak, and that are more prevalent. We're going to do this. We're going to test it in a companion animal dog model first. The reason why we're going to test it in a dog model is because dogs are the preferred model because their response and their immune system is very similar to ours as human beings, whereas opposed compared to a rat or a mouse model. And the other reason we want to do it for dogs is because I'm sad to say we all love dogs, it's a leading cause of their death after age 10. So it should be pretty easy for us to find people who want to enroll their dogs into a clinical study. So it's kind of like this perfect, it's the good model, and there's people out here who will do things for their dogs. We're going to develop we're going to develop a parallel companion immunotherapy program. And the reason we want to do it in there is because there's a lot of them. There's few treatments available. The options that are out there are very expensive, and they're just not very good. You could get 6 days of extended life, 6 months of extended life. It just is very variable. And the other reason we want to start off in dogs, or in the companion animal market, is because we can get to market quicker than we can going into humans. So what our ultimate goal is to set up an effective companion animal program, and then use that to jumpstart our human applications. So once we know that we've got a successful one that's working in animals, then we'll jump to humans and kind of run these in parallel, but the humans is going to be delayed probably a couple of years. We can get to market quicker on animals, and it'll take us longer to get to humans. But the ultimate goal is to have a successful companion animal one to help support our human model. We did a pro forma, or I did a pro forma for the company. Right now I did an estimated projected value of our companion animal lines at about 700 or 675 million. And human applications could be about $1.25 billion. This assumes on both of these a 7% long-term market penetration. Doesn't start off at 7%, it progresses up to 7%. We wouldn't start seeing cash flows until 2021. So we think it's going to take us about 5 years until we can start seeing cash flows in the companion animal model. Then for the human applications, same thing. We're only assuming a 7% market penetration rate. Cash flow is not starting until 2023. And then we have the price of the two listed there. One of the big things for us is as we become more efficient, as we become better at what we do, we become more efficient, we can lower our costs, which will be the big thing. Here's kind of a timeline and cash flows for us. So we would do right now, we would do a mouse study as just the continuation of what is our preliminary data now. We have mouse data that proves our theory, so we'd continue doing that. We'd finish establishing our vector core. We already have a facility up at the Sid Martin Bridge House, and basically what we would do is vectors it's another name for an AAV. We make these AAVs. We already make these. What we would do is we'd sell these. They're research grade. Very common. People buy them for $2,500 a pop. Any research institution. So since we're already making them for ourselves, we can, we already got the grill. So we're just going to make hamburgers to sell to people also as well. We'd start our preclinical grade for our dog study in about 6 months. Then we get into our dog study, and that will continue here. Red would emphasize money coming out. Green would emphasize money coming in. So we think we get our vector sales starting in about a year from now. And we're continuing with STTR grant funding, so it's a mechanism the NIH plays. We've already got a grant right now being reviewed. We're hopeful, but that's not a guarantee, but it would be a good way to get in cash infused in the company with no equity. And then once we've got really good dog study data is when we'll really start going after Series A funding from venture capitalists. Financial needs for the company at this point in time. To do our animal studies, we need $150,000. To continue the establishment of our vector core, we need about $250,000. To complete the dog studies, we need about $100,000. IP licensing, about $250,000, and $750,000 for operating expenses, which comes out to $1.5 million. It's kind of what we need for the next 30 months to get us through. What's unique about Aavet Therapeutics, the team, between myself and my partners, we've got over 40 years we've got over 40 years and 20, that was really poorly written. We've got over the combined years of 20 years in academic research. We've got 6 issued and or pending patents. And our patent protection for our company, which kind of prevents other people from entering our competitive field, is we've got it on the construction, the production, and the administration. So we've kind of got all 3 ways protected from someone else coming in here and copying what we're doing using our technology. It just can't be done. The team is the president, Dr. Richard Wagner. We've got our chief scientific officer, Dr. George Oslanidi, myself, and then we've got 2 staff scientists, Fido and Kelly. And then we also have a collaborator who's already willing to work on the dog studies with us. He's one of the most well-known people in veterinary cancer. His name is Dr. Jerry Post up in New York. He's willing to work with us as well. And that's it. So any questions you have and feedback, I'd love.
Except for that was about 13 minutes.
Oh, good. Good. I knew I wasn't going 20, so.
Okay. All right.
I thought it was a great presentation. I got